Hello, my name is Mack Gregory, and I'm an undergrad at the University of California, Davis. Professor Puckett is a professor of mathematics at the same. We would like to talk to you today about some recent advances we've found and made in modeling interfaces in viscoelastic flow properties in particles in geodynamic computations. So let's get started. Our motivation with our research is to develop models that are accurate and can represent the wide variety of processes and materials that go on in Earth's surface and mantle, whether that's the crustal deformation that we can see in this, or mantle convection, or any of the things that go along with that. To model this, we're using the Rayleigh-Benard equations, which give us a model of convection in the Earth's mantle. And what we're going to do with these is we're going to mention that we are not actually modeling temperature on this. So that lets us disregard the fourth equation for energy. And in equation 2, we don't have to consider the second term on the right because T and T0 will be the same, which really helps simplify this into an incompressible Stokes problem. To develop more complex methodology, though, we also need to consider rheological information such as viscosity, elasticity, and plasticity. And these equations on the right help to convey some of the more general equations that model the materials with a variety of the properties that together can form Earth. Aspect is an extensible community code written in C++ that supports all sorts of Earth and planetary processes such as convection and tectonic processes, as well as the rheological properties and other things like that we've already mentioned that are very important to our modeling. Aspect is already fully parallelized and includes adaptive mesh refinement that helps to make sure that researchers can compute efficiently on large three-dimensional domains and have very computationally large problems that aren't as computationally expensive as they might otherwise be. It's partially supported through the computational infrastructure for geodynamics at UC Davis. CIG is funded by the National Science Foundation to go and help create and disseminate this work. So let's take a look at our methodology. Many of the particle properties such as density, viscosity, stress, characteristic functions, they're vectored with the velocity field using the equation here from the previous page. And what we do with this is that at every time step, we're going to form a least squares problem, creating a plane using the particle positions and the particle property values. And then once we have formed that plane on the entire cell using least squares, or cell average, then we're going to transfer that plane and use that plane to create values onto the underlying grid and use that to participate in the solution at every time step so that things can go back and forth between the particles and the model itself. So you don't want it to just be a one-way talk, but a conversation between the two. So now we're going to get into some improvements that we're making on these so that we can have high-order accurate representations of the particle properties and so that we have a bound-preserving limiter to help keep overshoot and undershoot controlled. So what are these particles or particle and cell methods, you ask? Particles are now getting widely used in the computational geodynamics community to model a variety of processes that are passively transported within the flow field. So on the right here, we have a figure that's showing a subduction zone where we have a plate or fluid that is going down and other fluids are moving around and getting subducted. So you can then go and look at the coloring here to say where these particles had started. And you can really get to, if you examine this one for a long time, you can really start to tell how far some of these particles have potentially moved and how they're moving to go and model the western United States plates. There are 7 common particle interpolation algorithms that our collaborators in the geodynamics community already use. The simplest of which is the cell average interpolation, which purely takes the average of all the particles' property values in the cell. Right? Sums it up, divides it by the number of particles, and assigns it to any point that needs a value. And that works okay. It gets second order accuracy and it won't overshoot or undershoot. Then we have the linear least squares, we use least squares to fit a plane formed in 2D by C0 plus C1x plus C2y. And then we can get a little bit more accurate, which with a quadratic least squares, using instead of a linear equation, a quadratic equation here that we show that now has 6 terms. And that, again, is done with a linear least squares fit. But let's look at what that accuracy really looks like. In a recent paper from Renegas, Moeller, and as well as several other authors, we found that the linear least squares limiter, even when given a high-order accurate Stokes element combination, such as the Q3, Q2 used in this picture, where without particles we'd expect 4th-order accuracy, this only found a 3rd-order accuracy, and only then if they managed to use an increasingly large number of particles per cell. That at 4,096 particles per cell becomes rather computationally infeasible for things like 3D problems, let alone the 2D problem that this is being tested on. And if you would use less particles per cell, like the 4 that's shown, you only get 2nd-order accuracy, which is even worse. So this really demonstrates a need for the QLS, which is more accurate. The QLS, by comparison, we can use we can get 4th-order accuracy in this same fixed problem by using a particles per cell of 9 and keeping that fixed. And we see that it only deviates from 4th-order accuracy in this chart when it reaches an accuracy of 10 to the minus 12th, which is getting very close to machine error levels, such that we're really confident that the QLS, while it does suffer from overshoot and undershoot, just like the linear least squares, the quadratic least squares does very well on its accuracy on this problem especially. It's not possible to get rid of these overshoot and undershoots with these least squares based interpolators because of the high order accuracy that they have. So the only options that somebody is left with is either to go back to a low order accurate interpolation thing, like the nearest neighbor to the cell average, or to employ a limiter, which will take some of your accuracy away, but it will help you to stay within the property bounds that you know you need to be in and prevent things overshooting and undershooting it harmfully to your algorithm. So what we can do with this then is work on our limiter. And the limiter that we're working on now ensures that the value of the property is within the range on the cell without prior knowledge of the values that it should lie in. And we can prove that this statement will work and that our limiter will function correctly for 2- and 3-dimensional problems on rectangular grids. And a great thing to note about the implementation of particles and aspect is that you don't need, if you want to have multiple properties on your particles, you can, and you don't need to create a second set of particles for every additional set of properties. So to look at the linear least squares, we want to look at a model. And to start off our looking at models, we're going to look at this spherical drop in 2D. What's going on with these drops that we're going to show is that we have a red sphere that's got a relative density of 2 and a viscosity of 1,000. We've got a fictitious white material with a relative density of 0 and a viscosity of 1,000th. And we have the blue fluid that the sphere is falling into eventually with a density of 1 and a viscosity of 1. The entire computation domain is being covered with particles that carry the value of 2 different functions, chi s if the particle is initially in the sphere, and chi w if the particle is initially in the white material. Both of these functions are 1 if they're in the material that they should be, and 0 otherwise. So for example, if you're in the red, then I would expect that the chi s for sphere would be 1, and chi w for white would be 0. If you're in the white, I would expect that the chi s would be 0 and chi w would be 1. And if you're in the blue, then I would expect both chi s and chi w would be 0. So here's the video of that computation running. we see the particles are moving around in the white and creating vortices as it falls. On the left, we have the limited version, and on the right, we have the unlimited version. Something that we can notice with this is the color bar that we're going to use for most of the rest of today. And that color bar is going down to negative 0.63, and it's going up to 1.7. And if you remember correctly, I already mentioned that the function for the sphere indicator function should really be 0 to 1. So it wouldn't make sense that it's that large. So now we can look at the two drops with and without limiting here. Again, this is taken just as a frame from that previous video that we just showed. And right now you can't see very much extra on it, but what we can do is really get zoomed into that slide. So here we're looking at the top right corner of the sphere at time 37. So the sphere is already hit the water, and we're now looking at just the sphere and the surrounding blue fluid, and I've hidden the air to make this easier to see. So what we can see on the left at the limiting is that there's no overshoot or undershoot. And we can tell that because there's no dark red or dark blue spots, especially at the boundary, where the color bar would indicate that the value is above 1 or below 0. But if we look at the right instead, we see several spots along the boundary of the sphere that are overshot, undershot, and sometimes even both in the same cell. But if that didn't convince you of overshoot and undershoot, then this most certainly should. Here we're looking at the same kind of problem with a falling sphere, but the main change here is that the sphere is falling not from the white substance, but from the blue substance. So the boundaries between the white and blue are much more fixed and known, and they are not around the sphere as well. So what we see with this here is that we've plotted as the slope of this the values of the indicator functions. So on the left with the limiting, we see that there's no overshoot or undershoot along the edges of the sphere or at the boundary of the white material and the blue fluid. So, right, we can see pretty distinctly the cell edges where these things match up, and nothing goes above or below these cell edges. On the right, however, we go and see that there's quite a bit of overshoot and undershoot with that. There's all sorts of spots in there where you can see the red pointing up and into or above what it should be. And the same with the blue there at the top of or at the boundary of the blue and the white. So we can really point out there that that is overshooting significantly, and it undershoots significantly as well. So now we're going to look at a 3D computation of the falling drop. We can see that it starts from about the same position as we've been starting it in 2D, but now it has a third dimension, so it's still centered in the top, but we're letting it fall into the blue fluid, and it does that pretty quickly and then gets to sink in till time 100, just like the 2D models. With this off-axis view, we're able to see the entire sphere as well as half of the blue fluid, and that lets us get a little bit of a sense of how far it goes in. And then we can look at the same computation, but with all the particles being shown, and we can see how the sphere falls in and moves the white particles and the blue particles around to make room for itself. With both of them, we can recognize how the limiters worked in this, and that we don't have any overshoots or undershoots that can damage our computation. So some of the conclusions that we're drawing from this is that the quadratic least squares algorithm is eliminating the need for increasing particles per cell that they had found with the linear least squares as the cell size decreases. We've developed a limiter for this that will maintain the upper and lower bounds of the particle properties during the interpolation step for the linear least squares in 2 and 3 dimensions on rectangular grids without the a priori knowledge of what those bounds are. And it's the future work that we're working on is we're hoping to extend this limiter to spherical geometries as their modeled aspect. So thank you so much for your attention. Do you have any questions?